One stupid decision is abundant and limited. Is it two of them? When I was young, yeah, and then a lot of voters, and I was like, no, you're gonna. It's like no one. All of them. Oh yeah, that's good to know. Yeah, that was the local test. No, oh yeah, you have to trust it. I want to do something really honestly. Yeah. More time. Straightforward. Yeah. Because you already Is this the birth packet again?
Yes.
Yeah.
Guys, page 45. I just want to talk about problems where we have to deal with U substitution and definite integrals. But remember that anytime we see a definite integral, we know that our ultimate result is going to be something that is displacement related or area related. But the bounds is always the last thing we do, right? We never want to plug the bounds into the expression unless it's like a second theorem where there's a derivative and integral involved. Then we can skip that. We can skip the process of derivative and integrals and plug the bound in. But usually, if that's an integral problem and there's bounds involved, I know we want to read from left to right, but the bounds is the last thing that we do. So initially, we're going to ignore the bounds. We're just going to focus on the problem at hand. So that we can let's just rewrite it without looking at without the bounds, so we can just focus on our initial task. So technically, we could go through power rule. If we want to do power rule with this, well, what would we need to do? Yeah, expand it out. Takes a little bit longer, but typically anything that is higher than degree 2, you're not going to be expected to expand anything out. But you could. I mean, this won't take forever, but we do have we do want to explore another option, and that option is U substitution. This could work as well. U substitution works. What could be our U value?
X squared minus 2.
X squared minus 2. Let me underline that. And is this going to work out nicely in terms of the x's canceling out?
Yes.
Yes. Okay. So let's try that. Cross multiply, solve for dx. Our initial steps are trying to find a replacement for what we've underlined. Everything else we're going to rewrite. X's cancel out nicely. And the 2's cancel out nicely, so we don't have to worry about any coefficients in this problem. Okay, let's do our antiderivative. U to U cubed becomes what? Yeah, U to the 4 over 4. Now, once we're here, we know that we have to involve the bounds somehow, right? Because ultimately we have to plug in our upper and lower bound. But because these bounds, though, are in terms of what? What variable? In terms of x. but right now we have a temporary variable u. So one method, which I think would prefer, is we're going to bring everything back in terms of x, like how we normally would. So u becomes x squared minus 2. And then once we have our antiderivative in terms of x, we can plug in our upper and lower bound. The half bracket indicates that I'm ready to plug in my bounds. What value do we plug in first? Good, upper bound gets inserted first. We end up with 4 minus 1/4, which is 15/4. I want to show you one way of doing. I think this is the way. There's two methods. There's two ways of working the bounds into a u substitution problem, and this is one way to do it. This is the way that I prefer. I mean, because we're going to end up with x's, so bring everything back in terms of x, and then just use the original bounds. I want to show you a second method. Second method is we're going to hold on to this u to the 4th over 4. And instead of turning this back in terms of x, we can take the bounds and turn them into what? In terms of u, yeah. So the conversion is this equation here. U equals x squared minus 4. So I'm going to convert the bounds. And I think most of us are not going to prefer this method, but it is important for us to go through this because sometimes AP exam, multiple choice problem kind of has a setup using this method, and we need to be able to recognize how to involve a problem in this method. So to convert the bounds, I'm going to start with lower bound here. So if x is equal to 1, then my u value is x squared minus 2. So therefore, u is equal to 1 squared minus 2 is equal to -1. So my initial lower bound was 1. My new lower bound is going to be -1. Okay. My original upper bound is 2, but after I push it through the turn it into a different variable, my u is going to end up being 4 minus 2, which is 2. So I'm going to do u to the 4th over 4. My antiderivative is in terms of u. My upper and lower bound has also been converted to be in terms of u. Now we can plug in our upper and lower bound. (16 over 4 minus 1 over 4), we get the same answer, 15 over 4. Any questions? So ultimately, whenever you're doing u substitution with definite integrals, just make sure that your antiderivative variable matches the variable of your upper and lower bounds. Okay, either your antiderivative is in terms of x and your bounds is in terms of x, or your antiderivative is in terms of u and your bounds are in terms of u. Just make sure you're dealing with like variables. Okay, so that's one thing. Second thing, sometimes when you go through conversion of bounds, your lower bound all of a sudden ends up being a higher value than your upper bound. If that's the case, don't try to flip-flop it. Then just plug in whatever the lower bound starts off as, you're going to keep it as a lower bound. Don't try to suddenly try to change it. I mean, you could change it, but then you got to make sure you adjust with a negative. So if the lower bound ends up with a higher value, that higher value will still stay as a lower bound. Third thing I want to point out is when you're dealing with upper and lower bounds and something is out of order, it's okay. you can still go ahead and if this upper bound is a smaller value than your lower bound, you can still go through the process and get the answer that you want. I think really the only time I feel like I want to flip the bounds is if I'm reading a graph. If I'm reading a graph, I don't want to read from right to left because then above is negative and below is positive, and it just feels like I got to do a lot of adjusting in terms of keeping track of that. But if everything is done algebraically, then you don't have to flip the bounds. Everything will work out the way it's supposed to. But if you feel like you prefer the upper bound being the higher value, that's fine. Just make sure if you flip the bounds to allow that to occur, make sure you adjust it with a negative in front. But typically with this process, I don't really care if the upper bound is lower than the lower bound, but I do care if I'm trying to read the graph. Okay. And then finally, I want to point out that this is the wrong way of doing it. And this is sometimes students do this where they get to the u to the 4th over 4, and then they start using the bounds from the original. So this we want to make sure we don't do. Okay. Here, there's a mismatch of variables. And this happens sometimes because we don't go far enough and we involve the bounds. So if the bounds are in terms of x and then your antiderivatives in terms of u, then there's a mismatch, and that's not going to lead you to the right answer. Okay. So okay, any questions? Okay, I'm going to skip example 2. There's quite a few things I want to go over today. So if you guys are okay, we'll move on to even and odd function. So page 46, let's start at the middle here. The top is a review problem. So here's the property of even and odd function. The property says that if I have an even function, that means my graph is going to be a mirror image across my y-axis. So let's say I had a graph that looked like this from 0 to a. If I have an even function, I can create a mirror image on the other side as well. So the property says the depth integral from negative a to a is same thing as looking at half the region from 0 to a and then doubling it. So if the problem says this is an even function, if I can figure out the picture of the graph on one side of the y-axis, then I can duplicate that picture on the other side of the y-axis. And an odd function is going to be equal but opposite on both sides of the y-axis. So let's say there is a region from 0 to a. Let's say that region ends up giving us a displacement of 6. Then an odd function is going to be, as long as I'm the same distance away from the origin as the other side, I'm going to get equal but opposite displacement on the other side, which means that if I were to add up my regions on both sides of the y-axis, the same distance away, I'm always going to get 0. So if this is -8, this will be +8. If this is -9, this will be +9. So your even function will always double what you see on the other side. Your odd function will always cancel out what's on the other side. So I'm going to have us write down these 3 steps. I think these 3 steps will kind of help us organize our graph the best. So we can write this out here. So we're going to start with the shorter interval. And I'm going to talk about what this means in a second. You can write this down first. Second, we're going to fill out the other side. Using our even or odd properties. depending on what the problem is. And third, we're going to graph the larger region or the larger interval. Not necessarily the larger area, but the larger interval. That's the important thing. Whatever spans the shorter interval, we look at the bounds, not the area. Okay, so here's example 3. Suppose g of x is an even function. Okay, so we know how our graph's going to end up looking. If I can get, I can always work on both sides to get that duplicate mirror image to show up. I have one region from 0 to 3, area is 2, and then from -4 to -3, and the area is 4. Okay. Find the depth integral from -4 to 3 of g of x dx. Which one is the shorter interval? Good, this one here. I know this side has a larger area, but this is going to be the short interval. Now, sometimes it's not going to make a big difference, but I think this is the best way to kind of make sure that we don't accidentally miss something. I think this is the best way to kind of organize your information, especially for the more complicated problems. So let's graph what that could look like. So we want the region from -4 to -3 to show an area of 4. So I'm going to mark this off as -4 to -3. Mark this off. I'm going to create a mound here and call this area region 4. Okay. So we graphed our shorter interval. Now we're going to fill out the other side. Okay, so we're not going to do the larger interval yet. We're going to fill out the other side. So if it's an even function, what can we put on this side? From 3 to 4. Also what? A region of 4, right? Okay. Next up, we're going to graph the larger interval. Larger interval is from 0 to 3. 0 to 3 is equal to 2. In this problem, it doesn't really matter. What's going to be more difficult is if a larger interval overlaps the shorter interval, and we have to make sure that that we account for that. But right now, we're just practicing through these steps. So from 0 to 3, I'm going to create a region of 2. Which means that what can I do on the other side? Also 2. Region. Yeah, sorry, it's not even, but you get the idea. Now, we're going to add up the regions that the problem is asking for. It's asking for the depth integral from -4 to 3. What's that going to add up to be? 8. Oh, one thing to be careful. If the bounds are out of order, make sure you adjust them, because if it's backwards, then we got to change the sign of this, right? So sometimes you may be staring at an integral that may be backwards, and the number that you see is really the opposite of what's showing on the graph. So always pay attention to the bounds. Yeah, because we're reading graphs, we want to have the bounds in proper order. So if something's out of order, we do want to flip it. Okay, example 4. Same condition, but now it's an odd function. And we're still going to follow these steps here. Graph the shorter interval, fill out the other side using even odd properties, and then graph the larger interval. Again, the first 2 examples is really not going to matter the order that we do these things, but when we get to the third example, it's going to be really helpful doing this process in this order. Okay, what's the shorter interval here? Again, -4 to -3. As soon as I have my shorter interval built, I'm going to fill out the other side. What can I put on the other side now that it's an odd function?
3 to 4.
Mm-hmm. And what can I put there? Mm-hmm. Good. Now let's move on to a larger interval. We are reading from left to right, from 0 to 3. 0 to 3 equals 2. Which must mean the other side is going to have to be -2. Now that we have our picture all filled out, we're going to find the integral from -4 to 3. That'll add up to be what? 4. Okay, example 5. Even function. We have the region from 3 to 6. We have the region from -6 to 3. And we're trying to find the region from 0 to 6. Which one do we start building?
Six to 3.
3 to 6, right? This one here, first
Yeah.
one. Because that's a short interval, right? We always want to start with a short interval. Don't look at the area. Look at the width that the region is involving. Okay, what do we do after this?
Mirror.
Other side. Yeah, let's do the mirror image. Now this one, this is why we do it this way. It's because of this scenario when there's an overlap. There's an overlap from -6 to 3 equals 12. Now, I want to make sure that we understand that once we have something down, we're not going to make anything overlap it. This is set in stone. Okay, this is what some students want to do. Some students want to say, oh, -6 to 3, I'm going to call this whole region 12. Technically, that's true, but then you're overlapping this region, and then this is not really 7 anymore because you're putting something on top of it. And we don't want that. Okay, so just keep in mind that this means that everything added together within that region will be 12, but we don't want to step on a portion that's already set, right? So we can do this though. We can say, okay, when everything is added together from -6 to 3, it's going to have to add up to be 12, and we can fill in the gaps, right? If this is 7, then the remaining region has to add up to be what?
5.
To be 5. So, but it's an even function, so how do I split 5 up?
2.
2.5, yeah. So whenever there's an overlap, make sure that you leave alone the portion that's already been graphed, and you only fill out the part that has not been graphed. Okay, our final step, we're going to add the region from 0 to 6. That's going to give us what? 5. Okay, so that's really it with even an odd function. If you can follow these 3 steps, and then you don't try to overlap a region that's already set, then it should be pretty straightforward. Not any. The only trickiness with these types of problems is just watching out for the overlaps, but if you do it in this order, we'll have all the data we need so that we don't get tripped up by those overlaps. Okay, next page. So power rule works great for any situation involving x, but there's one exception. What if we try to do power rule with this problem? Yes, that's true. But let's just do power rule though. What happens if we, okay, let's say we wanted to attempt power rule with this. How would you set this up? This will x to the what? Yeah, x to the -1.
So it's undefined.
It's undefined because if I try to go through power rule, I'm going to add 1 to the exponent, which becomes x to the 0 over 0. We can't divide by 0. So this is the one scenario where power rule is not able to handle itself. So we have an exception for this, and the exception that can handle this is natural log. So if you remember, the derivative for natural log is u prime over u, right? Which is really 1 over u times u prime, right? Or natural log of x is just 1 over x. So it stands to reason that if we take the antiderivative of 1 over x, it'll bring us back to natural log. So that's the rule here. 1 over u du equals natural log absolute value of u plus c. This is basically the going backwards with the derivative rule for natural log. All right, let's try some examples here. Example 1, 2x over x squared plus 1. Remember, the first thing we should always involve and when we go through our checklist of integral rules is, can we do power rule? And this one, we can't expand and use power rule because why? There's multiple terms in the denominator. If there's only one term below, then I would rely on power rule. Okay, but as soon as there's one term more in the denominator, we're forced into something else. Okay, and the second thing is there is no such thing as quotient rule for integrals. So I see some students try to do quotient rule, that doesn't work. So our next option after power rule expansion is use substitution. And in this case, we see a potential candidate for u value, and that u value is going to be x squared plus 1. So let's go through that process. U equals x squared plus 1 du dx. Cross multiply. Solve for dx. Okay, make our substitutions. Do we have our x's canceling out? Yes. So we're left with integral of 1 over u du. And this matches perfectly with the rule that's available to us, which is natural log absolute value of u plus c. And u is only a temporary variable, so we got to bring back our original variable in terms of x. Let's see. Sometimes, though, example 2, we have problems where the u value is not as apparent. And we have to do a little bit of kind of trial and error and guess and check to get our way there. So if I want to go through, well, first off, we can't do expansion with this one, right? There's too much going on. So we got to go through substitution. So is the u value going to be just the x? Is it going to be just the natural log of x? Or is it going to be the whole denominator x natural log of x? So the issue is, if we have the whole denominator being the u value, then the derivative is going to have to go through a product rule, and that's going to create a whole mess that the rest of the problem doesn't have enough support to cancel out. So that's a little too much. Just natural log of x. So here's the thing. If we just let the u value be natural log of x, the derivative of natural log of x is 1 over x, and that 1 over x will handle that x that's waiting for it. Right? Again, it's, the more problems you do, the more you're going to be able to kind of predict what could be a good U value. But as you guys are getting used to that, it's also a matter of, okay, if you go down the wrong path, can you catch yourself? Are you able to catch up? Are you able to see the context clues where things are not working out because you don't see a nice pairing? If you don't see a nice pairing, you want to go back and reconsider a different U value. So here's our U value. U is natural log of X. Natural log of X, the derivative for natural log of U is U prime over U. So 1 over X, cross multiply, dx equals X du. Make my substitutions. X's cancel out. We're left with 1 over U du, which is natural log absolute value of U plus C. Replace the U back in terms of X. Natural log of absolute value of natural log of X plus C is our answer. Let me do a related problem. I'm going to put this to the side here. If you have room, I'm going to call this example 3. Two x over x squared plus 1 quantity squared. Power rule can't do this problem. There's too many terms below. We got to look at U substitution. What could be our U value? Squared plus 1. Okay. Okay. X's cancel out, very much like example 1. I end up with 1 over U squared du. How do I handle this problem? This one is what? Power rule, right? But what do you think a lot of students want to do with this problem? Natural log. Because I think the tendency is we see enough of the U variable in the denominator, we're going to feel, oh, anything in the denominator is going to be a natural log. It just feels easier, right? But this is only reserved for when the U value is raised to what power? 1. If it's any other power, you got to bring it up and go through power rule. Okay? So that's a trouble spot for students. We want to make sure you're aware of that. That it even though power rule is what we're potentially more comfortable with, once you see that U in the denominator, you're going to just naturally want to go through the natural log rule because it just feels like, oh, it's easier. Oh, easy, 1 over U, I'll just do natural log. But any other power, if it's U to the 1/2, U cubed, we got to bring it up to the top. We got to go through power rule. Even though in this case, natural log feels easier and faster, but it's only going to work if it's the correct power. Okay. All right, let's look at bottom of the page here. Okay, completing the square and long division are 2 skills that help us manipulate integrand until it becomes something that we can work with. We can practice these 2 skills. I'm not going to do long division. I'm going to do synthetic division. I just haven't seen any problems on the AP exam that requires long division. So we're just going to stick with synthetic division. It's going to be the faster route. So how do we know whether something requires this process of synthetic division? We go through our checklist for this problem. Number one, first thing is, can we expand using power rule? Power rule. What's the issue here? Yeah, there's multiple terms in the denominator. So if it was just x or x cubed or 2x squared, then we want to split up into individual parts and just rely on power rule. X minus 2 is causing an issue here. Second is, our second option is u substitution, but can you imagine a u value above or below that's going to help pair up with the other side? Doesn't quite work, right? So when our degree is higher than the numerator and lower than the denominator, this is going to be a good candidate for synthetic division. Now, synthetic division is not going to solve the problem for us. It'll just present the problem in a different form, which will allow us to rely on mainly power rule and natural log to get to our answer. So the way that we can divide this is we can go through synthetic division. So the first thing you do is set the denominator equal to 0 and find a factor for that denominator. And that factor is 2. You're going to put 2 outside a half box. And you're just going to put the coefficients of each of the terms to represent each degree. So we're starting off with degree 3. What represents degree 3? 3. Next column is for degree 2. What represents degree 2? -1. Next up, degree 1. Finally, we end up with a constant, which is 1. Now, if a degree is not represented in the numerator, we need to have a placeholder. We need to put a 0. So let's say it was just 3x cubed minus 5x plus 1, then it'll be 3, 0, -5, 1. If it skips over a degree, we need to have a placeholder 0 to represent that column. Okay, next step. You're going to drag the first number below the line. Okay, next up, multiply. 2 times 3 is 6. Put that number in that second row above the horizontal line, and then you're going to add. -1 plus 6 is 5. Okay. Repeat the process. 2 times 5, 10. Add 5. Multiply 10. Add 11. Okay. Now we're dividing by x. So if we're dividing by x, every degree is going to fall by 1. So this started off as 3x cubed. After the division, this is now going to be what? 3x squared. So 3x squared. And then every term is going to fall by 1 degree. Plus 5x plus 5. And guess what this is called? It's the remainder. Okay. So your remainder is indicating I can't divide any further. It's not going to divide evenly. So because I can't divide any further, I'm going to have to indicate 11 divided by x minus 2 is not resolved. So that's going to be the last term. My remainder is the portion that doesn't divide evenly, but I have to indicate that's what's left. What's left over is 11 divided by x minus 2. Now, this is not the answer, but this is the same value as the starting fraction. But the nice thing about this is that every term is separated, and we can just rely on power rule to get to our answer, because before we had all this connection through fractions that we're not able to resolve. Now we have basically independent terms. Save for that last one where we can just go through a bit of use substitution and natural log to get to our answer there. Okay, so we're going to apply our integral rule 4 times, once for each term. 3x squared becomes, what's power rule there? Yeah. Yeah. Plus 5x squared over 2 plus 5x. Now this is its own problem. there's a little bit of u substitution here. What could be our u value for this mini problem, 11 over x minus 2 dx? Yeah, x minus 2. Right? My u value is x minus 2. My derivative is 1. Dx equals du. I'm left with integral of 11 over u du, which is the same thing as 11 integral of 1 over u du, which is natural log. So plus 11 natural log absolute value of u. I'll skip a step here, replace the u back in terms of x. And then don't forget plus c at the end. Okay, can we practice this process for number 2? Use number 1 as a model to help you through your steps. But I just want to make sure. Oh, wait, hold on. This is not. Oh, that's messy here. Find a better one. Here, let's change that denominator to just be x minus 5. We're not going to have to deal with that messy fraction there. Okay, let's try number 2, but just change that denominator to x minus 5. Okay, let's try that, and I'll work through it at the same time you guys do. Sorry for these large numbers. One last thing that I want to quickly show you. I forgot to talk about exponential function e to the u. So can you turn back to page 45? I want to use example 2 space to talk about e to the u here. Page 45. So what's the derivative of e to the u? Yeah, e to the u times u prime. So it stands to reason then, what's the antiderivative of e to the u? Yeah, good. So because the derivative is itself, then integral is also itself. So the rule for e to the u du is just e to the u plus c. So sometimes you have problems that has e in it, and typically, if it's a messy problem, your exponent is your u value. Let's try this problem here. Integral of x times e to the 1 minus x squared dx. This doesn't fit into any of the rules that were available to us, but if we can think in terms of, oh, if we let our u value be 1 minus x squared, then the derivative should handle that x, and that should match this rule. If we can make it match this rule, I can find an integral for that. Let's try this one. Okay, so what's our u value? Yeah, 1 minus x squared. We'll save that x for the derivative to cancel out. The x's cancel out, which is great. It's a good sign. But we got to keep track of what? Negative 1/2. Okay, so we take the antiderivative of e to the u, the negative 1/2 stays. So e to the u, integral of e to the u is just what? Just e to the u. And then replace the u back in terms of what goes in the exponent? 1 minus x squared.
Say that the integral is e to the u plus c.
Yeah.
You have to distribute the 1/2 to the c.
Yes.
Barely went off.
Yeah, but the 1/2 times c is just c, so it's not wrong if you did that, but typically we should leave that plus c. Yeah. Okay. Your homework, check your calendar. There is AP practice. Some of you guys showed me AP practice already, but yeah, AP practice for 5 point, yeah, for 6.5 is probably your homework for the weekend. All right, can you get your phones?
Number 6.4.
Yeah. Thank you.
That's where it starts.
Okay, great. Thank you.
Thank you.
No, you don't. If you see that, oh, that's an easy knack law, you turn from here to here, and that's fine.
I had a question. This one, this 45. So, on this one, like for example, if it was 1 on top and 2 at the bottom, it would still be bigger minus the smaller one, right?
And it's
regardless of where, like what, if 1 is not.
Yeah, so if 1 is above and 2 is below, you still want to plug into 1 first.
Oh, you want to put in 1 first?
Yeah. If you want to, if you feel like the order matters to you, and you want to see the higher number above, you can flip the bounds. If you do that, just make sure you put a negative in front.
Okay.
Yeah.
It would be the right, so to get the right answer, you have to put in the top one first and smaller.
You don't have to. So if I, let's say I had x to the 4, and I want to evaluate it from 1 to 2. 2, 1, then I gotta follow one of these things. If I don't like this, then we can do that.
Okay. I know it probably won't be on my schedule.
But we can't just flip the bounds and not do anything. So if the bounds are the way it's supposed to, you gotta plug in the one first.
So I did.
But if you don't like to plug in the lower number first, and the bounds, just make sure you
You said
3 months. This unit seems pretty easy so far. 3 months. Triangles and rectangles. I'm saying this unit seems pretty easy except for Raymond's lines.
And I just didn't know.